அனைவருக்கும் இனிய காலை வணக்கம். I, Dr. R. Mangayarkarasi, Assistant Professor, EMG Yadava Women's College, Madurai, Kotti. Today in differential equation, we are going to see block 3. In block 3, we are having second and higher order ordinary differential equation, unit 10 and unit 11. Unit 10 என்ன இருக்குன்னு பார்த்தோம்னா higher order linear differential equation. Unit 11 method of undetermined coefficients. So notation symbols are used in this block 3. D double dash of y, where capital D denoted as a differential operator d by dx. Here d power ny, that is nth order derivative of y with respect to x. And then you are having f of d, that is nth order polynomial in d, that is f of d equal to a0 d power n plus a1 d power n minus 1 plus a2 d power n minus 2 plus etc. Your last term will be plus an. This is called as nth order polynomial in capital D or nth order linear differential operator. And you are having the Wronskian. This W symbol is denoted as a Wronskian. That is W of y1 of x, comma y2 of x, etc. yn of x. This Wronskian play a very major role in this differential equation. And especially in block 3, we are using this Wronskian. That is W of y1 of x, etc. yn of x denoted as Wronskian of n functions. What are those n functions? y1 of x, etc. yn of x. C dot f denoted as complementary function. P dot I denoted as a particular integral. So LHS, here these are all the notation, that is abbreviation we have used in this block 3. LHS left hand side, RHS as right hand side, kg means kilogram, m means meter, second, and cm centimeter, E means electromotive force. These notations will be used in the terms of the application of differential equation. So electromotive force, capital R is the resistance, capital L is inductance, C is the capacitance, Q is the charge, I is the current. Okay, some Greek alphabets will be used in this block 3. Sigma, zeta, epsilon, tau, pi, and omega, and delta, and psi. Now in the first block, in block 3, first 10th section, we have used higher order linear differential equation. 10.1, we are concentrated on introduction, objectives, and general linear differential equation, solution of linear differential equations, conditions for the existence of a unique solution, properties of the solution of linear differential equation. And then homogeneous linear differential equation with constant coefficients. And then we have some exercise and with the solution. Introduction. In block 2, we defined the basic concepts related to ordinary differential equations and discussed various methods of solving first order ordinary differential equation. We also formulated and solved some of the physical problems which were governed by the first order linear ordinary differential equations. The methods developed there required mainly the skill in the techniques of integration, and the equation could be solved in terms of familiar elementary function. However, this may not be the case always. As mentioned in the introduction to this blog, the differential equation governing many physical or biological phenomena may not necessarily be the first order. There may be the higher order linear or nonlinear equation may have constant or variable coefficient. Now, in this section, general linear nth order differential equation into two broad categories. The first category has homogeneous and non-homogeneous. Second one, equation with constant coefficient and variable coefficient. Here we shall mainly confine to the method of finding the complete solution of linear homogeneous differential equation with constant coefficients of order 2 or more. Non-homogeneous equation will be considered in the units to follow. It is usually much more difficult to solve the equation if the coefficients are not constants but variable. We shall not be discussing the method of solving such equation in this course. However, for a general linear differential equation with variable coefficient, we shall state in section 10.3 the conditions under which a unique solution can be found. We shall also discuss here some properties of solutions of linear differential equations and define its general or complete solution. The methods of finding complementary function of a linear homogeneous differential equation with constant coefficients are discussed. At the end of this unit, we have given in an appendix a brief review of some of the concepts from matrices and determinants, which you will find useful while going through the properties of the solution of linear differential equation. Now, the main objectives once you go through in block 3, after reading this unit, you should be able to identify linear differential equation with a constant as well as with variable coefficient. Identify homogeneous and non-homogeneous linear differential equation. Describe the condition under which a unique solution of linear differential equation exists. Write the complete integral of a given differential equation when its various independent integrals are known. And then classify solutions of non-homogeneous equation into complementary function and particular integral. And then obtain the general solution of homogeneous linear differential equation with a constant coefficient. These are all the objectives once you go through block 3. Now, general linear differential equation. Let us begin by considering the following equation. D squared y by dx squared plus 2 into dy by dx plus 2y equal to 0. And d squared y by dx squared minus 3 into dy by dx minus y equal to x plus 2. What is the difference between these two equations? Now, you know that both the equation are second order linear equation with a constant coefficient. The only difference being the term x plus 2 on the right hand side of the second equation, which is a function of x plus a constant term. Such a term called the non-homogeneous term makes the equation non-homogeneous. Now, consider an equation of the form. See that this equation, the second equation you are having in the right hand side, x plus 2 will occur. This will denote the non-homogeneous differential equation. And then now consider an equation of the form x square d square y by dx square plus 2x dy by dx plus 3y equal to x square plus x plus 1, where the coefficients are functions of x. Note that it is also a second order non-homogeneous linear differential equation with variable coefficient. The most general form of linear differential equation is given in the equation 1, that is a naught of x d power n y by dx power n plus a1 of x d power n minus 1 y by dx power n minus 1 plus etc. plus a n minus 1 of x into dy by dx plus a n of x into y equal to b of x. This is the equation number 1. Now, in this equation, the coefficients namely a naught, etc., a n and b are continuous on an interval alpha comma beta. If a naught of x is not equal to 0, then we can say that this differential equation is of nth order. So, equation 1 is a linear differential equation of nth order with variable coefficient. Now, in case a naught, etc., a n are all constants, that is, they do not depend on x, then equation 1 will be termed as a linear differential equation of nth order with constant coefficients. Now, see here further, when b of x equal to 0, in that case, the equation 1 is classified as homogeneous linear differential equation. And then we come to the point of non-homogeneous linear differential equation. If b of x not equal to 0 and is a constant or a function of x, then the equation 1 termed as a non-homogeneous linear differential equation. The term b of x is the non-homogeneous term of equation 1. In studying the non-homogeneous equation 1, it is necessary to consider along with it the corresponding homogeneous equation obtained from it by replacing b of x by 0. Such an equation is called an reduced equation associated with an equation 1. See here in that equation 1, you are having in the right hand side, you are having b of x. If we reduce this equation as b of x equal to 0, this equation is a non-homogeneous equation. If b of x may be a constant or a function of x or a variable coefficient, then we can call this equation 1 as a homogeneous equation. Now, for an example, you consider an equation d cube y by dx cube minus 4 into d squared y by dx square plus dy by dx plus 6y equal to 0. This is a third order linear homogeneous differential equation with constant coefficient. Now, you come to the equation d power 4 by y by dx power 4 plus 4 into d cube y by dx cube plus 3y equal to x square plus 1. This is a linear non-homogeneous equation of fourth order with constant coefficient. Now, the corresponding reduced equation as d power 4 y by dx power 4 plus 4 into d cube y by dx cube plus 3y equal to 0. So, if we put this right hand side will be equal to 0, the homogeneous will be reduced to a non-homogeneous equation. Now equation x cube d square y by dx square plus x square dy by dx plus xy equal to 2. This is a second order non-homogeneous linear differential equation with variable coefficient. Now you must have noticed that the context in which the word homogeneous used here is totally different from used in this unit 6 in block 2. Now classify the following differential equation into homogeneous and non-homogeneous equation and write the reduced equation corresponding to non-homogeneous equation. See the first equation, you are having y triple dash plus xy double dash plus x squared y dash plus x cube y equal to log x. This will be log x. Your answer will be, this is a non-homogeneous equation because you are having the term of right hand side. And the reduced equation, you make the right hand side will be equal to 0. The reduced non-homogeneous equation will occur. Now come to the second equation, y triple dash plus 2y double dash minus y dash equal to 2y. Now this equation is a homogeneous equation because there does not exist any term in the right hand side. Now come to third equation, 1 minus x into y double dash plus xy dash equal to y plus 1 minus x the whole square. This is again a non-homogeneous equation, and the reduced equation will be, you have to bring this 1 minus x the whole square as 0. You have to bring y in the right hand side, you have to bring to the left hand side. So that the reduced equation of a non-homogeneous as 1 minus x the whole into y double dash plus x into y dash minus y equal to 0. This is one of the typical example for homogeneous and non-homogeneous equation. Now definition, a set of functions y1 etc. yn is said to be linearly dependent on an interval I if there exists real numbers c1 etc. cn not all zeros such that their linear combination, that is c1 y1 of x plus c2 y2 of x plus etc. plus cn yn of x equal to 0 for every x in the interval. So linearly dependent means this constant, namely c1 etc. cn not all 0, it is linearly dependent. If all the constants c1 etc. cn are equal to 0, then linearly dependent will be modified as an linearly independent. Now we come to that linearly independent definition. A set of function y1 etc. yn is said to be linearly independent on an interval I if it is not linearly dependent. For linearly dependent, the necessary condition will be the constant are not all 0. For linearly independent, all the constants will be equal to 0, then it is called as a linearly independent set of function. Now example, determine whether the function cos squared x, sin squared x, secant squared x and tan squared x are linearly independent or linearly dependent on the interval minus pi by 2, pi by 2. Solution, let us consider, now given the functions are cos squared, sin squared, secant squared, tan squared, they are all the trigonometric function. You have to write a linear combination of all those trigonometric functions, that is c1 cos squared x plus c2 sin squared x plus c3 secant square x plus c4 tan square x equal to 0. Now we are choosing the point, choosing the constant, namely c1 equal to 1, c2 equal to 1 and c3 equal to minus 1, c4 equal to 1, for which this equation will be equal to 0. So if you are substituting c1 equal to 1, you are having cos squared x, and then c2 equal to 1 cos squared x plus sin squared x. Okay, this cos squared x plus sin squared x equal to, you are having an identity as 1. And again, if you choose c3 equal to minus 1 and c4 equal to 1, here you come across the value for minus 1. This come to another identity. So this 1 and minus 1 will join together will make us 0. Therefore, this equation, namely the c1 cos squared x plus c2 sin squared x plus c3 secant squared x plus c4 tan squared x equal to 0, satisfy the point c1 equal to 1, c2 equal to 1, c3 equal to minus 1, c4 equal to 1. Therefore, this equation satisfied by those constants in the interval minus pi by 2 to pi by 2. Therefore, all the constants will be not equal to 0. Therefore, the given functions are linearly dependent. And then show that the function e power x and e power 2x are linearly independent on any interval. So we have to take as a linear combination of the given function as c1 e power x plus c2 e power 2x equal to 0. So for all x in the interval. Now we must show that c1 equal to c2 equal to 0. So let us take two distinct points in this interval, namely x0 and x1. We then obtain a homogeneous system of equation. These 2 points satisfy that linear equation, namely c1 e power x0 plus c2 e power 2x0 equal to 0. and C1 e power x1 plus C2 e power 2x1 equal to 0. So you have to eliminate the two constants C1 and C2. Therefore, the determinant of the coefficients, namely e power x0, e power 2x0, e power x1, e power 2x1, you have to find the determinant. Determinant will be equivalent to e power x0, e power 2x1 minus e power x1, e power 2x0. So you have to bring e power x0, e power xn outside. Inside the bracket, you are having e power x1 minus e power x0. This is not equal to 0 in the interval since these 2 points are a distinct points. Namely, x1 and x0 are you have to taken as a 2 distinct points. Therefore, x1 will be not equal to x0. Therefore, this determinant will be not equal to 0. Therefore, we know that your knowledge of linear algebra, if the determinant of the coefficient not equal to 0, the only solution of a homogeneous system in the interval is trivial. That is, we must have C1 equal to C2 equal to 0. Therefore, the given function, namely e power x and e power 2x, are linearly independent on any interval. This is another way we have to identify whether the given functions are linearly dependent or linearly independent. Next example, check whether the set y1, y2 of a function of a given interval is linearly dependent or independent in the given interval. First example, y1 equal to e power x, y2 equal to e power minus x in the interval minus infinity to plus infinity. First, you have to write as a linear combination, and namely c1 e power x plus c2 e power minus x. This is equal to 0 for every real x. Only when this equation will be satisfied only when C1 0 and C2 0. If C1 0 and C2 0, then the given functions are linearly independent. Now come to second example. You have to take the functions are y1 equal to 2 cos 3x and y2 equal to 3 sine of 3x plus pi by 2 over the interval minus infinity and plus infinity. Here you have to write as a, these two are a dependent one. Therefore, we have to write this 2c1 cos 3x plus 3c2 sine 3x plus pi by 2. This is 2c1 cos 3x plus sine of pi by 2 plus 3x will be modified as cos 3x. Okay, so we have to bring cos 3x outside, which is satisfied for any non-zero choice of C1 and C2, for which this 2C1 plus 3C2 equal to 0, then C1 equal to minus 3 into 3 by 2 into C2. Therefore, the given two function, namely 2 cos 3x and 3 sine of 3x plus pi by 2 are linearly dependent since the constants will be not equal to 0. Now we come to the third example, namely y1 equal to e power x, y2 equal to x into e power x. If we write a linear combination of y1 and y2 with the help of the two constants, namely c1 and c2, then that is this linear combination will be equal to 0 and all the constants will be equal to 0. Then only this linear combination will be 0. That is c1 equal to 0 and c2 equal to 0. Then only the given linear equation, namely e power c1 e power x plus c2 x into e power x equal to 0. Therefore, the given function, namely y1 and y2, are linearly independent. Next theorem, suppose y1 etc. yn are n functions on the interval I possessing derivatives at least up to n minus 1th order, then we have to write a determinant. This w will be already be introduced in the notation. W is a Wronskian of the given functions y1 etc. yn. This Wronskian will be defined as a determinant of the first row will be given function, second row will be first derivative of the given function, second derivative, etc. up to how many derivatives? N minus 1th derivative. Is non-zero for every 1 point in the interval I, then the functions are linearly independent on I. This is a very important theorem based on this linearly independent and dependent based on the Wronskian. If the Wronskian will be 0, then the given functions are linearly independent. If the Wronskian is non-zero, then the given functions are linearly independent on I. If the Wronskian will be 0, then it is linearly dependent. The proof for this theorem, for simplicity, we consider the case when n equal to 2 and prove the theorem by contradiction. Now let us assume that w of y1, y2 of x0 not equal to 0 for some x0 in the given interval, and that y1 and y2 are linearly dependent on that interval. Then since y1 and y2 are linearly dependent, there exists a non-zero constant, namely c1 and c2, for which their linear combination, namely c1 y1 of x plus c2 y2 of x equal to 0 for every x in I. Now evaluating this expression in the derivative at x0. So C1 y1 of x naught plus C2 y2 of x naught equal to 0. Then C1 first derivative, C1 y1 dash of x naught plus C2 y2 dash of x naught equal to 0. So you have to bring these two equations in the form of a Wronskian. The linear dependence of y1 and y2 implies a system 2 possess a non-trivial solution for C1 and C2. Therefore, we have to write a Wronskian of y1, y2 of x naught, that is equal to y1 of x naught, y2 of x naught, y1 dash of x naught, y2 dash of. We have to find a determinant of this 2 by 2, the coefficient. This determinant will be equal to 0 for every x naught in I. But this is a contradiction to our assumption that the Wronskian will be non-zero. Hence, we conclude that y1 and y2 are linearly independent. So, we have proved the result for n equal to 2. The result for n function can be proved on the similar line, but we shall not go into details here. So for the case of n equal to 2, we have proved that the system of equation, namely the y1, etc., yn or n function on an interval I possessing derivatives will be existing up to which order, n minus 1th order. Then if the determinant, you have to write a Wronskian for this n function. Then if the Wronskian is non-zero, we have to take that those n functions are linearly independent. Here we come to that example. Show that y of x is equal to 3 into e power 2x plus e power minus 2x minus 3x is a unique solution of the initial value problem. That is y double dash minus 4y equal to 12x with the help of the initial conditions y of 0 equal to 4, y dash of 0 equal to 1 on any interval containing 0. Here we have to say that the given function y of x have a unique solution. See here we have y of x equal to 3 into e power 2x plus e power minus 2x minus 3x. Therefore, you have to find a first derivative, y dash. What is y dash? You have to e power 2x differential, again e power 2x into 2. Therefore, 6 into e power 2x. Again, you have to differentiate e power minus 2x. That is e power minus 2x into minus 2. And then the minus 3x, x will be differentiated as 1. Therefore, this is equal to minus 3. Therefore, y dash will be 6 into e power 2x minus 2 into e power minus 2x minus 3. Again, you have to find a second derivative, namely y double dash equal to. Again, 6 into e power 2x differentiate. Again, e power 2x differentiate as e power 2x into 2. Therefore, 2 into 6, 12. 12 into e power 2x. Again, minus 2 into e power minus 2x differential as minus 2 into e power minus 2x. Minus 2 into minus 2 plus 4 into e power minus 2x. Minus 3 differential will be equal to 0. Now, in the problem itself given that y double dash minus 4y equal to 12x. So, you have to find a y double dash minus 4y. You have to arrive the result of 12x. Therefore, y of x satisfy the given differential equation. Now, we have to find the initial value. What is y of 0? It comes to value for, you have to substitute in y of x equal to 0. And then y dash, we already found y dash of x. In y dash of x, make a substitution, x equal to 0. Therefore, y dash of 0 again equivalent to 1. So, these two are the initial conditions satisfied by y of x. Therefore, the given equation y of x equal to 3 into e power 2x plus e power minus 2x minus 3x is a solution of the given initial value problem. Moreover, the given differential equation is linear and all its coefficients are a constant function and hence continuous on any interval containing x equal to 0. Also, this a naught of x will be not equal to 1, which is not equal to 0 on any interval containing x equal to 0. Therefore, we conclude that the given function y has a unique solution of the given initial value problem. Now, this is the way to give the function has a unique solution for the given initial value problem. So, this is one of the best example for that. Next, we are having shown that if y1 equal to x squared, y2 equal to x squared log x are both the solution of this equation on the interval 0 infinity, then for arbitrary constants c1 and c2, y equal to c1 x squared plus c2 x squared log x is also a solution of the equation on a given interval. So what is, we have to prove that if y1 and y2 are the solution of the given differential equation, and what is c1 and c2 with the constant c1 and c2, then y equal to their linear combination is also a solution of the given interval. This is a very important example based on this above theorems. main application related with the above theorem. That is, if the given function or the solution of one differential equation means their linear combination is also a solution of the given interval. That is a concept based on this example 6. Now solution. If y equal to c1 x squared plus c2 x squared log x is a solution of the given equation, then it must satisfy the equation. Now let us check whether this y satisfies the given equation or not. We have y dash. What is y dash? Already we are having y equal to what? C1 x squared plus C2 x squared log x. We have to find y dash. So that is, you have to differentiate x squared 2c1x and then x into here in the above that you are having x squared log x. We have to differentiate x squared log x in the form of UV form. That is 2x log x plus x squared into 1 by x. That is the differential of d of x squared log x. Therefore, this is 2c2x log x plus c2x squared log x differential as 1 by x. So, after simplify this is equal to 2c1x plus 2c2x log x plus c2x. And then y double dash, you have to differentiate again. That is 2c1 plus 2c2, that is log x plus 2c2x into 1 by x. And then last term is plus c2x, that is c plus c2. That is equal to 2c1 plus 2c2 log x plus 3c2. Okay. So y triple dash will be 2c2 log x differential as 1 by x. Therefore, 2c2 by x. 3c2 will be equivalent to 0. Now substituting this y dash, y double dash in the given equation, that is x cube y triple dash minus 2x y dash plus 4y. You have to substitute all those values. And then further simplification, the result arrived at will be equivalent to 0. Therefore, your linear combination, namely c1 x square plus c2 x square log x, satisfy the given equation, and hence this is a solution of the equation with the given interval. So note a point that if the individual function or a solution of the given differential equation, then their linear combination is also a solution of the given differential equation with the given interval. That is a point note down from this example. Next, theorem 3. If y1 etc. yn are solution of the differential equation on an interval I, then the linear combination is also a solution of the given equation with the arbitrary constant. Now let us prove the theorem when n equal to 2 for the second order equation. That is a naught of x y double dash plus a1 of x y dash plus a2 of x into y equal to 0, having y1 and y2 as its two solutions. Since y1 and y2 be the two solutions of this given equation, we have a naught of x y1 double dash plus a1 of x y1 dash plus a2 of x y1 equal to 0. Similarly, the same given differential equation satisfied by the function of y2. That is why we have written a naught of x y2 double dash plus a1 of x y2 dash plus a2 of x y2 equal to 0. And we know that c1 y1 plus c2 y2 the whole dash is equal to c1 y1 the whole dash plus c2 y2 the whole dash. That is equal to c1 y1 dash, because c1 and c2 are the constant values. So we won't differentiate this c1 and c2. So that is equal to c1 y1 dash plus c2 y2 dash. Similarly, c1 y1 plus c2 y2 the whole double dash. Double dash will be due as c1 y1 double dash plus c2 y2 double dash. If we define y equal to c1 y1 plus c2 y2, then a naught of x y double dash plus a1 of x y dash plus a2 of x y will be equivalent to 0. We have to arrive there after simplification, after substituting all those given equation, this arrive at equal to 0. That is y also the satisfy the given equation. Therefore, if y1 and y2 are the solution of the given equation, then their linear combination, namely y equal to c1 y1 plus c2 y2 is also a solution of the given equation. Now example 7. Show that for the differential equation y triple dash minus 6y double dash plus 11y dash minus 6y equal to 0. Here you have to verify the theorem 3 holds true for the function y1 equal to e power x and y2 equal to e power 2x, y3 equal to e power 3x on the interval minus infinity plus infinity. You can easily check the function e power x, e power 2x, e power 3x all satisfy the given homogeneous equation. Therefore, the function y equal to c1 e power x plus c2 e power 2x plus c3 e power 3x should also satisfy the given equation for the arbitrary constants C1, C2 and C3. Now y dash. What is y dash? Here we know y1, y equal to C1 e power x plus C2 e power 2x plus C3 e power 3x. Here we have to find the first derivative y dash. And then we have to find a second derivative and then third derivative. Substitute all those values in the given equation. Finally, we arrived y triple dash minus 6y double dash plus 11y dash minus 6y equal to 0. Therefore, the linear combination of the given function, namely C1 e power x plus C2 e power 2x plus C3 e power 3x, is also a solution of the given equation. Therefore, the theorem 3 holds true for the function in the given problem. Finally, we have a conclusion that if the functions are the solution of the given differential equation, then their corresponding linear combination is also the solution of the given differential equation. Next example 8. Show that y1 of x equal to sin x, y2 of x equal to cos x, y3 of x equal to x, y4 of x equal to 1 form a fundamental set of solution of the equation y fourth derivative plus y double dash second derivative equal to 0 in the interval minus infinity plus infinity. Also write the general solution of the equation. Now solution, consider y1 of x equal to sin x. What is y1 dash, y1 double dash, and then y1 triple dash, y1 4 dash. So you have to substitute all those four values in the given equation, namely y4 dash plus y double dash equal to 0. Substitute a value, it will be equivalent to 0. Therefore, then y1 of x equal to sin x is also one of the is a solution for the given differential equation. Similarly, you can check for y2, y3 and y4. All those will satisfy the given equation, and hence all those three values, namely y2, y3 and y4, are the solution of the given differential equation, namely y4 dash fourth derivative plus y double dash equal to 0. Now we have to check the linear independence of the given function, namely y1 of x, y2 of x, y3 of x and y4 of x. We have to consider the Wronskian, that is, if the Wronskian will be equal to 0, it is the given functions are the linearly dependent. If the Wronskian will be not equal to 0, the given functions are linearly independent. So you have to consider the Wronskian of the given four functions, namely sin x, cos x, and then x, and then 1. So you are having the four functions given in the given problem. y1 of x equal to sin x, y2 of x equal to cos x, y3 of x equal to x, y4 of x equal to 1. For those given functions, we have to create the Wronskian, that is w of sin x, cos x, and then x, comma 1, that is equal to determinant of, you have to write a first row will be the given variable, given functions, that is sin x, cos x, x1. And then you have to write a derivative for sin x, cos x. Cos x as minus sin x. X will be differentiated as 1. And then 1 differential will be equal to 0. And then again you have to find the second row, you have to find the derivative, cos x minus sin x, again minus cos x. 1 differential will be equivalent to 0, 0 as 0. Again you have to find a fourth row as a differential of the third row, that is minus cos x, again minus cos x as sin x, 0, 0, 0. You have to find a determinant of those values. You have to arrive the result as this is will be the identity sin squared x minus all those three values will be 0. The last one is minus 1, minus you have to bring outside, that is plus 1. Into inside the bracket you are having an identity sin squared x plus cos squared x. The identity will be equivalent to 1. Totally this Wronskian will be equivalent to 1. This is non-zero for the interval minus infinity, infinity. Therefore, the given function, namely y1, y2, y3 and y4, they form a fundamental set of solution on the interval minus infinity, infinity. Therefore, the general solution of the differential equation on the interval as y equal to c1 sin x plus c2 cos x plus c3 x plus c4 into 1. Now our next example, show that y1 equal to e power 3x and y2 equal to e power minus 3x form a fundamental set of solution of the given equation y double dash minus 9y equal to 0 in the interval minus infinity plus infinity. Further, you have to verify the theorem for the solution y equal to 4 sin h 3x, that is hyperbolic function, and then minus 5 e power minus 3x on the given equation. Now we are going to find a solution. Given y1 equal to e power 3x, that is y1 dash, you have to differentiate 3 into e power 3x. y2 equal to e power minus 3x. And here y1 double dash 9 into e power 3x. This y1 dash, y1 double dash, you have to substitute a value in the given equation, namely y double dash minus 9y. That is y1 double dash minus 9y1. That is equal to, what is y1 double dash? 9 into e power 3x. Again minus 9 into what is y1 equal to again e power 3x. That is e power 3x. So this value get vanished. Therefore, y1 double dash minus 9y1 equal to 0. So we conclude that y1 is a solution of the given equation, namely y double dash minus 9y equal to 0. Similarly, we have to verify y2 is also a solution of the given differential equation, namely y double dash minus 9y equal to 0. Substitute y2, that is y2 double dash minus 9y2 equal to 9 into e power minus 3x minus 9 into e power minus 3x. Both value get cancelled. Therefore, this is equal to 0. Further, you have to find a Wronskian of the given functions, namely e power 3x, e power minus 3x. You have to find a determinant. First row will be e power 3x, e power minus 3x. Second row will be differential of the first row. That is 3 into e power 3x minus 3 into e power minus 3x. This determinant will be equivalent to 6 minus 6. Again, this is non-zero. Therefore, for every value of x, the given function, namely y1 and y2, are the fundamental set of solution of the given interval. General solution of the given equation in this given interval as y equal to c1 e power 3x plus c2 e power minus 3x. c1 and c2 are constants. Now we have come to the answer for the another question, namely you have to verify the theorem 5 for the function y equal to 4 sin h 3x minus 5 e power minus 3x on the given equation. Now consider y equal to 4 sin h 3x minus 5 e power minus 3x. We have, for this y, you have to find a value for y. We have to substitute this y in the given differential equation, namely y double dash minus 9y. That is equal to, substitute what is y dash? Y dash equal to 4 cos h 3x into 3 and then minus 5 into minus 3 e power minus 3x. So that is equal to 36 sin h 3x minus 45 e power minus 3x minus 9 into, got again substitute a value y. After simplification, all those values get cancelled. Therefore, this value will be equivalent to 0. Therefore, we conclude that y is also satisfy the given equation. Therefore, now choosing c1 equal to 2 and c2 equal to minus 7. Now we are having the general solution y equal to c1 e power 3x plus c2 e power minus 3x. You substitute a value for c1 and c2. So finally we arrive the value for 2 into e power 3x minus again 2 into e power minus 3x minus 5 into e power minus 3x. So this is equal to, you have to bring 4 outside. This value sin h 3x will be the hyperbolic function. Hyperbolic sine function has the value, has the identity sin h 3x equal to e power 3x minus e power minus 3x divided by 2. So you substitute a value. Therefore, this y also satisfy the given equation. Therefore, theorem 5 holds true for the solution of the given this. Next example 10. Now solve 2 into d square y by dx square plus 5 into dy by dx minus 12y equal to 0. The auxiliary equation for the given equation 2 into m squared plus 5m minus 12 equal to 0. For this auxiliary equation can be factorized as 2m minus 3 into m plus 4 equal to 0. Through this factorization, we have to obtain the value for m equal to 3 by 2 and m equal to minus 4. Therefore, these two roots are real and distinct. Hence, a complete solution of the given differential equation as y equal to c1 e power, the first root 3 by 2 into c1 and c2 are arbitrary constants. The next example, solve d power 4 y by dx power 4 minus 4 into d cube y by dx cube plus 8 into d square y by dx square minus 8 into dy by dx plus 4y equal to 0. This is the fourth order differential equation. So first you have to write an auxiliary equation. That is m power 4 minus 4 into m cube plus 8 into m square minus 8m plus 4 equal to 0. This equation can be factorized as m squared minus 2m plus 2 the whole square equal to 0. You have to obtain the root for this equation in the form of minus b plus or minus square root of b square minus 4ac divided by 2a. So once you got this, you have to obtain the two solution are m minus of 1 plus I the whole square into m minus of 1 minus I the whole square equal to 0. Through this factorization, we are obtaining the roots of m equal to 1 plus I, comma 1 plus I, that is 1 plus I occurring twice, and 1 minus I also occurring twice. These roots are the complex roots and repeated in this case. Therefore, we have to write a general solution as the two roots are repeated means you have to write in the combination of C1 plus x into C2. And then first root e power 1 plus I into x. Again, the third and fourth roots are repeated. Therefore, you have to write as a linear combination of C3 plus x into C4 into e power 1 minus I into x. That is equal to e power x into C1 plus x C2 into e power 1 plus I into x can be split as a two component. One is e power x, the another one is e power ix. And then e power 1 minus ix can be split as e power x into e power minus ix. So in both the term, you are having e power x will be common. So you have to bring e power x outside. Inside you are having c1 plus x c2 into e power ix plus c3 plus x c4 into e power minus ix. So e power ix value as cos x plus I sin x. And e power minus ix, you have to substitute as cos x minus I sin x. Therefore, you have to you have to separate as a real part and imaginary part. The first real part as e power x into, inside you are having c1 plus c3 plus x into c2 plus c4, then cos x plus I into, inside the bracket you are having c1 minus c3 plus x into c2 minus c4 into sin x. So the first value a plus bx, a will be c1 plus c3, b will be c2 plus c4, and then c will be what? I into c1 minus c3. What is d? D will be I into c2 minus c4. So you have to substitute, you bring the value as in the form of e power x into, inside the bracket you are having a plus bx into cos x plus c plus dx into sin x. So all those values, namely capital A, B, C, D are all constant values. So before that you are having this example 19, example 10, you are having this 2 into d squared y by dx squared plus 5 into dy by dx minus 12y equal to 0. Here with that any examples will be given in the form of a cubic equation, namely 2 into d cube y by dx cube plus 5 into dy by dx minus 12y equal to 0. Suppose you are having the cubic equation. So in that case, you have to write auxiliary equation as 2 into m cube plus 5 into m minus 12 equal to 0. This is second order equation we are obtaining as 2 into m square plus 5m minus 12 equal to 0. But in the third order equation, namely d cube y by dx cube, you have to write auxiliary equation 2m cube plus 5m minus 12 equal to 0. You have to factorize. How to factorize this value 2m cube plus 5m minus 12 equal to 0? Randomly, you have to substitute a value m equal to 0. M equal to 0 won't satisfy this equation. So you have to substitute a value m equal to 1. So in that case, this equation won't be satisfied. You have to substitute randomly m equal to 1, m equal to. For the cubic equation, first you have to find one factor. After that, that equation will be divided by that factor. Again, you have to reduce the cubic equation in the quadratic equation. For the quadratic equation, you have to find the roots for this quadratic equation as minus b plus or minus square root of b squared minus 4ac divided by 2a. That is a as the coefficient of, that is a x squared plus bx plus c equal to 0. That is a quadratic equation. Then that a, what is a as the coefficient of x squared. What is b as the coefficient of x and c as the constant. So in this way, you have to substitute a value in this formula. You have to obtain again another roots for that equation. So totally you are having 3 roots, and those 3 roots can be assembled in the form of an equation. The roots, if the roots are all real and distinct, then you are having the version of y equal to c1 e power 3 by 2 into x plus c2 into e power minus 4x. That is c1 into e power alpha x plus c2 into e power beta x. If you are having another root, suppose this is the concept if the roots are all real and distinct. Then you have to write a complete solution for this. Y equal to C1 e power 3 by 2x plus C2 into e power minus 4x, where C1 and C2 are arbitrary constants. So here you are come across another example, namely y1 equal to e power 3x and y2 equal to e power minus 3x. Suppose you are having one more function will be given, y3 equal to some e power 2x. So these three form a fundamental solution of the third order equation, namely y triple dash minus 9y dash plus minus 9y equal to 0 in the same interval. So in that case, you have to find y1. You are having three functions. What are all the three functions? Y1 equal to e power 3x and y2 equal to e power minus 3x and then y3 equal to again e power 4x. So in that case, you are having your equation will be third order equation, namely y triple dash minus 9y dash and then minus 9y equal to 0. For you first substitute a value for y1. Y1 you have to find a first derivative. Y1 as e power 3x. So what about y1 dash 3 into e power 3x? What about y1 double dash again 9 into e power 3x? And then y1 triple dash, that is 9 into 3, that is 27 into e power 3x. So you substitute in the given differential equation and then you got whether this y1 dash, y1 double dash, y1 triple dash satisfy the given equation, namely y triple dash minus 9y double dash minus 9y equal to 0. If that y1 satisfy the given differential equation, then y1 is the solution of the given differential equation. So in that way, you have to substitute y1, y2 and y3. If all the three values will satisfy the given differential equation, you have to substitute all these three values separately. So you should not substitute at a time. First, you substitute a value for y1 and then you have to substitute a value for y2 and then you have to substitute a value for y3 in the given differential equation. If all three functions are satisfied by the given differential equation, then you have to write a general solution. So in this way, you have to find a solution for that and this. Here come across another example, namely given the three values y1, y2 and y3, y4, they form a fundamental set of solution of the equation y4 dash plus y double dash equal to 0. Also write a general solution of the given equation. So you have to substitute one by one. So just you call y1 of x equal to sin x. You have to find y1 dash of x. Sin x differential as cos x. And then y1 double dash of x. Again cos x differential as minus sin x. Again minus sin x differential as sin x cos x. Already you are having one minus sign. Therefore y triple dash will be minus cos x. And then y4 dash. Y4 dash will be equivalent to sin x. So, since y triple dash will be minus cos x, again cos x differential as minus sin x. Already you are having minus sign will be that. Therefore, y4 dash will be equivalent to sin x. Now, substituting these values in the given differential is given as y4 dash plus y double dash equal to 0. This differential equation existing in the interval minus infinity to plus infinity. So, first you have to substitute a value for y1 4 dash and then y1 double dash. What is y1 4 dash? That is equal to sin x. What is y1 double dash minus sin x? Therefore, sin x minus sin x will be equivalent to 0. Therefore, the given function, namely y1 of x, satisfy the given differential equation. Next one, y2 of x. What is y2 of x equal to given as cos x? y2 dash of x minus sin x. y2 double dash of x. What is y2 double dash of x? That is again equivalent to y2 of x cos x. y2 dash will be minus sin x. y2 double dash again will be minus cos x. And then y2 triple dash will be equivalent to again sin x. So in this way, again substituting all y4 dash. y4 dash plus y double dash. If you substitute a value, this will be cos x minus sin x. Again, this will be equivalent to 0. Now you come to y3 of x equal to x. Therefore, y2 of x satisfy the given differential equation. Therefore, given function y1, y2 are the solution of the given differential equation. Now come to third variable, namely y3 of x. What is y3 of x equal to x? What is y3 dash of x? 1. So remaining the from second derivative onwards, the value will be equivalent to 0. Namely, y3 double dash equal to 0. y3 4 dash will be again equivalent to 0. Therefore, your given differential equation y4 dash plus y double dash. Y dash, y3 dash will be 1. Y3 double dash again 0. Y3 triple dash again 0. Y4 dash again 0. Therefore, the given differential equation y4 dash plus y double dash, the substitute a value, both the value will be 0. Therefore, 0 plus 0 will be equal to 0. Therefore, y3 of x again satisfy the given differential equation. So far, we verified y1 of x, y2 of x, and y3 of x. Now come to y4 of x. In y4 of x, the value will be equivalent to 1. Therefore, y4 dash. What about y4 dash? That's again equal. First derivative itself equal to 0. What about all the remaining derivative? All the derivatives will be equivalent to 0. Therefore, substitute y fourth derivative plus y second derivative. Both the value will be equivalent to 0. So, again y4 of x equal to 1 satisfy the given differential equation. Yes, we got a point. I hope this y1, y2, y3 and y4 all four the functions are satisfy the given differential equation. Y fourth derivative plus y second derivative equal to 0 in the interval minus infinity to plus infinity. So after obtaining the solution of this, you have to obtain a linear independent. Whether they are linearly dependent or linearly independent, then only you can able to write a general solution of the given equation. So you have to verify the linearly independent. You are having four functions, namely, what are the four functions? Sin x, cos x, x and 1. So for those functions, how to verify the linearly independent means, you have to verify linear independence of the given four function through Wronskian. What do you mean by Wronskian? Wronskian is nothing but a determinant of the first given four variable or in the first row. The derivative of the first derivative will be in the second row. Second derivative will be in the third row. Fourth derivative will be in the fourth row because we are having four functions. So the Wronskian will be 4 by 4 matrix you have to create it through this Wronskian. Okay, got a point? So y1 of x, y2 of x, y3 of x, if you are having two variable, if you are having two function, you have to create 2 by 2 Wronskian matrix. If you are having three function, you have to create a 3 by 3 Wronskian matrix. The Wronskian will be a square matrix. Suppose you are having four function, the Wronskian will be 4 by 4 matrix. See here you have to find a Wronskian because after finding a solution of the given, if the functions are all satisfy the given differential equation, after that you have to check the linearly independence. The linear independence can be checked through Wronskian. What do you mean by a Wronskian? You have to find a determinant of the given functions. That first row will be the given functions, second row will be the first derivative of the given function, third row will be the second derivative of the given function, and then fourth row will be the third derivative. If you are having four function, you have to up to third derivative you have to find out. If you are having two function, you have to obtain one derivative. If you are having three functions will be that. You have to create 3 by 3 matrix. How to obtain a 3 by 3 matrix? That is the question. So through 3 by 3 function, first row will be, you have to just write a 3 functions. And the second row, you have to find a first derivative of the 3 function. And then third row, you have to find a second derivative. So for 3 by 3 function, you have to obtain 3 by 3 Wronskian. If the Wronskian will be non-zero, then the given functions are all linearly independent. Then you can able to write a solution for the given function. Okay, got a point? Here you have to obtain the Wronskian of the given functions are sin x, cos x, x, comma 1. For these four functions, you have to obtain the 4 by 4 matrix. 4 by 4 determine you have to obtain. How to obtain the first row, second row, third row and fourth row we are going to see now. Now how to obtain the first row? First row will be just you write a given functions are in the first row. And the second row you have to write a first derivative of the given first row. And the second row, you have to obtain a second derivative. For the first derivative, you have to obtain a second derivative. For the second derivative, for the fourth row, you have to obtain a third derivative. Okay, first derivative will be second row. Second derivative will be third row. Third derivative will be the fourth row. See here, we are having 4 by 4 matrix. How to obtain determinant for this 4 by 4 matrix? See here, in the first row, the fourth column, first element will be 1, all the remaining element will be 0. So you have to reduce this 4 by 4 into 3 by 3 matrix. What is the 3 by 3 matrix? Cos x minus sin x 1, and then minus sin x minus cos x 0, minus cos x sin x 0. So see here, in this 3 by 3 matrix, third column, namely 1, 0, 0, two element will be 0, only one element out there. For this one element, you have to find the determinant. The determinant will be minus sine squared x and then minus cos squared x. This determinant you have to bring minuses outside. Inside you are having an identity sine squared x and then plus cos squared x. This sine squared x plus cos squared x has the identity 1. Therefore, determinant has the value of 1. This is not equal to 0 for every x in the interval minus infinity, infinity. Therefore, the given function, namely sin x, cos x, and then x1, all those functions, they form a fundamental set of solution. And since these functions may play a major role on linearly independent, therefore we have to obtain a general solution of the differential equation on a given interval, namely y1 equal to y equal to c1 sin x plus c2 cos x plus c3x plus c4. So in this way, we have to obtain a general solution of the given equation. So see here I am having the another example, namely that is y triple dash minus 6y double dash plus 11y dash minus 6y equal to 0. Now in this 10th and 11th section, mostly we insist the point of if a given individual functions or the solution of the given differential equation, then the corresponding linear combination. What do you mean by linear combination? You are having the functions are e power x, e power 2x, e power 3x. These three independent functions may be written in the form of a linear combination as c1 e power x plus c2 e power 2x plus c3 e power 3x. This linear combination will be treated as y of x. So if three individual function, namely e power x, e power 2x, e power 3x satisfy the given differential equation, namely y triple dash minus 6y double dash plus 11y dash minus 6y equal to 0, then the corresponding linear combination, once again I insist the same point, namely c1 e power x plus c2 e power 2x plus c3 e power 3x also satisfy the given differential equation, namely y triple dash minus 6y double dash plus 11y dash minus 6y equal to 0. That is the main concept we are concentrating in this section 10 and 11. That is the main concept. And then we come across this theorem. This theorem will be the major role throughout this section. y1, y2, etc. yn are solution of the differential equation on the interval I, then the linear combination. What is the solution? Differential equation will be nth order differential equation, namely this a naught d power n y by dx power n plus a1 d power n minus 1 by dx power n minus 1 plus etc. The last term will be the constant term. So that is equal to 0. Therefore, you have to treat this equation will be the differential equation, and this differential equation satisfy the solution of y1 etc. yn, then their linear combination, that is c1 etc. cn are some constants, arbitrary constants. So I have to write a equation linear combination as y equal to c1 y1 plus c2 y2 plus etc. plus cn y power n. This is also a solution of the given differential equation. Now this concept will play a major role, that is main concept, as if the functions are solution, then the linear combination is also a solution of this differential equation. So here we are having an example of this y1 equal to x squared, y2 equal to x squared log x. These two are both a solution, then their linear combination is also a solution of the given differential equation, namely x cube y triple dash minus 2xy dash plus 4y equal to 0 in this interval 0 infinity. For any arbitrary constant you have to take, you have to connect the given function with the arbitrary constant c1 and c2, and therefore y can be written in the form of c1 x squared and c2 x squared log x, and this linear combination satisfy the given differential equation, namely x cube y triple dash minus 2xy dash plus 4y equal to 0. And this differential equation satisfy the individual function as well as satisfy. If the individual functions satisfy the given differential equation, then the corresponding linear combination is also satisfied by the given differential equation. So that is, we have to write, we have to find y dash, y double dash, y triple dash. All these three values satisfied by this given differential equation. That is x cube y triple dash. Okay. So I close this session. Thank you. Nandri.